Sorry, I was logged on a little bit late. I just found out my nephew, who's living with us, slept late, and I realized it just before time for him to go to the bus. So it was time to start class, and I didn't. I was just not prepared. So sorry about that. Uh,
No worries.
this class is basically just me introducing the first lab of this course. Remember, this is an online lab. I want to remind everybody that TCC has made sure put it out in writing, and we're supposed to put it in our syllabus. And I've tried to tell people verbally that an online lab, a lot of universities are not necessarily accepting. So just to remind anybody, in case they didn't see the discussion about it last night on in class. I haven't posted that video from last night either. It was too long, and it takes me a little bit more time to edit it than I had last night. So I'll be posting that today, and this will go up on my YouTube channel as well. Do y'all have any questions before I get started? Right, and you can just speak up if y'all have a question, or you can type in the chat, or you can, wave me down with various little icons that you can post in the chat or whatever. So I'm not as familiar with Zoom as I really should be because I literally use it at least 4 days a week, and I'm always using it from the instructor standpoint, not from the audience standpoint. So I don't know all the bells and whistles that you can use to actually participate in a Zoom meeting. So I'll just say vague phrases like an emoji you can put up in chat. But anyways, I'm going to go ahead and share my screen. I'm specifically going to show you the Canvas page so you'll see exactly where the lab stuff is, and then I'll go over the lab's material by itself. So let me start off by sharing the screen. And again, ask me questions if you have any. I just want to remind everybody, this is our Canvas page. Notice it says PHY 241001B, summer 26, 10-week semester. So this easy drop area, you won't see it. It's just where I put stuff. Actually, all that stuff's bad, and it just copied over. I didn't even need this particular module. This module is the generic one that TCC is having everybody's courses have on them. So that just tells you a lot of stuff about the student handbook, the academic calendar. You can buy your course materials. Respondus Lockdown Browser going to be explained there. All sorts of good stuff. Critical thinking, using AI responsibly, knowledge. All this information is really, really good stuff. I highly recommend you looking over it as needed, and especially the stuff regarding AI. As I told you, I think I told you last night. But I know I told my face-to-face class, I had a student last semester who was doing a really good job, and she was really making use of AI, but she felt like maybe she used it too much because she ended up having grades that were not as high as she's used to, getting, C's instead of A's and stuff like that. So uh, learn from her experience and learn from these things that TCC offers, specifically using AI responsibly might be very, very helpful to you guys. Uh, After that, you'll see this is the helpful documents and links, the things I want to point out on there that are in there. I'm going to do more of this in my syllabus later. But right here, I'm going to have a new one put up today, but it says my video list by Austin. Austin's my oldest daughter, but it'll have a newer date on it, and that'll have everything I've made up until probably today. I'll probably have today's podcast in it, or excuse me, today's video in it as well. Here's a video you're supposed to watch just to remind you of the importance of the syllabus. And I don't know why. I think this is the right syllabus. I'm pretty sure I put it here, but I'm not sure yet. So the syllabus is already in this link right here, but I plan on putting a Word or PDF version right here. I think these are all the ones from the previous semester where I copied this course over. That's why it's not highlighted. Uh, these are the allowed equations for Physics 241. Uh, you should probably go ahead and make a printout of it and start using it and looking for any boo-boos. I know, for instance, there's one typo in it. You might be able to find that, and that's an important thing to notice. But anyways, have that sheet out whenever you're doing your homework problems or your practice tests, because that'll get you in the mood of being able to use this equation sheet when it comes to test time, because that's the information you'll get on your test. You'll also get these things that you see right here, these are all things that I put at the bottom of the test, or I'll put in a pamphlet that my students have when they take the test. And it's basically the inside covers of Giancolli's textbook. So it has more math formulas, a moment of inertia table, a periodic table, and then it has other fundamental constants like G, gravitational acceleration, or G, the gravitational constant of the universe. In addition to all of that, uh, this is a ironic video where I teach you that if you click on one of these things, see the little chain, that means a internet link. So if you click on it, inevitably what happens when you're going to my YouTube channel is it doesn't load. So let me share that real quick. But it's funny because I made it this way to teach teach you how to deal with it. But there's no way you can watch it until you learn how to deal with it. So when that happens, when you click on a link to one of my YouTube channels, it's gonna do this. It says YouTube refused to connect. That happens every time. I'm sure it's some security issue that they set up. All you have to do when that pops up is you go up here or here, but I usually click right here on this thing, and then that will bring you to the actual YouTube video that you're looking for. Okay. Of course, YouTube has commercials in it, but that's what we get for having free services like YouTube. So, anyways, that's what that is. I just want to make sure you guys are aware of that. I'm going to go back to modules now and just tell you that's what you got to do whenever you try to click on one of my links and it gives you that sad face. Uh, Here's my YouTube channel link and here's my Google Docs link. So the YouTube channel has these videos, and most of the videos, at least videos for lectures, have that code down at the bottom. You'll see it in this list right here for videos that I've made. You'll see a code and then you'll see a link. The link is what you click on to go to it. The code is the code that I put in the box at the bottom. And what that allows you to do is you can take part of that code, usually like the last let's see, 4, 5, 6, 7, 8, usually like the last 8 digits. And you can just put that in my Google Docs, the last 8 digits of that code, and it will do a search. And when you get that, it'll spit back the notes for that particular video. So you can actually download a PDF copy of the notes for any of the videos on my website or on my YouTube channel. So that's why we have the Google Docs link. There's another one for 242 as well, but you guys are only in 241, so you don't need it. All right, here's the invitations to the Zoom meetings. I think you obviously found this one, which is the 8 a.m. to 9 a.m. I didn't put this in everybody's class because I'm not treating this one like an office hour. This schedule was my intent to come in every morning at 8 a.m. Tuesday and Thursday to do your lab. But I did that specifically knowing that I've got a lot of things going on right now, and Tuesdays and Thursdays and Fridays are the days I try to use for getting my family to doctors and stuff. I've got elderly people and very young people, and people that have been injured living with me, so I want to take them to doctors when they need to be. So if I ever have to attend a doctor's appointment, I will either make the video early or make it late or something like that. That's why I didn't want it to be a bona fide office hour. But I will try my best to be there every day at 8 a.m. to sign in for it. All right, that's enough on the background stuff. So let me jump down to week one. You see, week one, this is what I was telling everybody. This is what you should go to every Monday. Usually I have it posted by first thing Monday morning, but I guarantee it'll always be posted by 5 p.m. So if you only have one chance to go, then wait till after 5 p.m. But either way, that's what you should do when you go into Canvas is first go to modules and then look at the week that you're working on. For instance, May 18th to May 24th, it's May 19th. So clearly this is the week that we're working on. You'll see a ton of videos that are here, and then you'll see the homework links here and other things that you have to do. Like you have to do a syllabus copy and paste. I got to change that due date, by the way, as well as some of these I might have to change. No, it looks like all these dates are okay, but that one I got to change. But anyways, if you look on a week's module, like this week's module, and you do all of these assignments that are listed here, and these are just extra credit. You don't have to do those, but you can. Then you've done everything that's required for this week. There's no other assignments that you have to do other than these. Okay, so please, please, please always check this every Monday. And don't worry about if you go over in these other places. You can go to different places in Blackboard and find assignments that aren't in these modules. I don't know how they got there. I don't know where they are, and I haven't been able necessarily to find them all. But I know students every semester are like, why do I got to do this? Why am I getting a zero for that? For starters, there's nothing in the grade book that I have that would cause your grade to go down if it can't be seen in the module. So every assignment that is in your grade book and actually affects your grade are the ones that are in the actual module. There's no grade impact for anything that's not found in the module. That's why I'm telling you your your module is the sort of the source for knowing what work has to be done. So far, you can see this is just chapter one. That's because we're pretty much assuming chapter one is going to take most of the week. However, I might be able to fit in a little chapter two next week if that's our next class period. If that's the case, then I'll put some more chapter two assignments up here as well. All right. These are the two extra credit assignments we talked about last night, but what I'm going for now is the lab. So this is our week one lab module. I haven't changed the dates. I thought I did that last night, but evidently I did not. So I'll change them in a second. But either way, it's for the same week that this one above is. And this is the intro to lab. So this is the actual document that you're going to use as your lab report. So the way we're doing lab reports in this course and many of the ones that I teach in general is I have a Word document that you guys download right here, and you download it, and then you basically follow the procedure step by step, but you also read very thoroughly step by step every part of the lab. So if there's a paragraph in the lab somewhere and it asks you a question, then what you're supposed to do is take your cursor and put it right to the right of that question mark where they asked you the question, and then hit return, 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 and then in the middle of that white space, you type in an answer in some font other than black. That should happen with every question that the author of the lab asks. You should answer it. Okay. You should fill in every blank that it has in there, unless it's a blank that's not applicable. Then you put NA in that blank. Anytime it tells you to print something, what you should interpret that as is to take a screenshot of that thing and then paste it into the document. And when I say screenshot, I mean taking a photo of the screen or part of the screen. If you take a photo of your whole screen and you got a big screen and then you stick it on a Word document, the actual part that I'm supposed to look at is likely going to be way too small. So make sure when you do paste a photo or paste anything like that, none of the font is smaller than 12 points. Okay, so 12 point font is about the smallest you should turn in. If I see it any smaller, I'm definitely going to take off points. It just makes it hard for me to see. So I just want you to do that. Make sure, if you have a one screenshot that you've cut out everything except for the graph and the data table, and then you post that in, there's a good chance that that's not going to be good enough because you put the graph and the data in there. That usually takes up so much room. It makes the data, the numbers that I need to read on the graph and in the columns, it usually makes them too small. So it'd be better to make two separate ones, and each of them be a little bit bigger. We're not printing these lab reports out, so it's not like we're wasting paper. We're not wasting any paper. It's all e-space or electronics space. So you do that. When you go into this turn-in area, there are copious instructions about what to do. So let me click on that right quick. This is also where you're going to turn in the lab. So it says Lab 1, Enter to Lab. Generally, each weekly module will include a lab document for that week. The lab document will be in Word format, and you can download it in the lab report, in the lab, in the computer or to your own computer or tablet. Okay, so it's a generic one that I do for my labs for both face-to-face and online. So that's why it mentions stuff about you can download it in class. So if you choose to only download one copy to the lab computer, you will need to duplicate data tables, so on and so forth. Again, that's for the people that are meeting face-to-face. If any question is asked in any part of the lab document you downloaded, you should put your cursor to the right of the question mark, hit return, slash enter three times and then type the answer in a font that is not black. So you can see all that stuff I was just telling you is right here. I just wanted to make sure you knew that. And this is where you'll actually turn in a document, and you see it only takes a PDF file. So as this explains right here, what you're supposed to do is not only answer every question, not only fill in every blank, not only put in the graphs or whatever it tells you to print. Make sure you put that in the document right where it asks for it. Don't save everything to the end. That's why I keep saying right where it asks. Do not put all your graphs and data at the bottom. That's not helpful for me. It doesn't help me be able to grade. So I want to put right where the manual actually said for you to do it, or the manual told you to do it, not necessarily just at the end. Okay. Now, once you've inserted all those sample calculations, remember every type of calculation that is done in a single lab has to have a sample calculation of that type. So when I say type, I mean literally type. So if you have a one part of the lab, you have to take the length of a aluminum rod, say, and you measure it 5 times, and then you, of course, you take the average of that 5 times of those five ones, and that's your best estimate of that length. When you do that, though, that length is now. Uh-oh, hold on a second. It just something just popped up on my computer. Okay, that's weird. All right. All right, now, sorry, just a bunch of messages popped up on my screen. I don't know what it was. I think it's some spam stuff, or anyways. Uh, but when you actually do make the measurements and everything, you're going to then take those five measurements, take an average, and then you're going to report that value. But when you report that value, you need to do it in a color of font that's not black if you type it. If you handwrite it, that's fine. But not only that, that is a sample calculation. You've now computed an average of five links. So that's one of the sample calcs that you'll write down. You might choose to show me that particular average calculation. And when you do that, you start off with the formula for the average, which would be the summation from I equals 1 to n of x sub I divided by uh, big N. So that's the formula for average, and then you fill in the individual data with their units, and then you compute the answer. That's your sample calculation. Now, if later in the lab you have to, measure the mass of something 5 times and calculate an average, you don't have to show a sample calculation for that because you're calculating an average. We just did that. The same thing with percent difference or percent error. If you showed me one sample calculation using the simple or using the percent error formula, then you don't have to show it for any more. Same thing with the percent difference formula. You don't have to show it anymore. So one of each type. But like if you have to calculate a kinetic energy, then I need to see one of those. If later you have to calculate another kinetic energy, I do not need to see a second one. Now, once you've answered all those questions, filled in all those blanks, printed all those things, and done a sample calculation for everything, and you filled in the data tables, and you got your results, and you leaned on the side of giving me more graphs than they asked for, as opposed to less graphs than they asked for. Once you've done all that, you've got this Word document that's got all this stuff pasted in it. What you're going to do then is put your name in the title of it. So, for instance, Billy Younger could be B Younger, Lab 1. That could be the title of the document. So you save it as, B Younger Lab 1. You can put underscores between the B and the Younger and the Lab 1 stuff if you want, or you can just butt them all against each other and just use capitals to separate them. The main thing is I want to see your name in the file name. You're going to save it as it is. Then you're going to do save as, and when you do save as, you're going to choose a PDF to actually render that. So you're going to save it as a PDF document, and that's what you're ultimately going to turn in is that PDF. And it should be one PDF. I don't want four PDFs because you've got one for the lab report and one for this thing you printed out, and one for this other graph. No, there should be one PDF document, and everything is in that. And I open it and I read it from the top to the bottom, and anything that you put in would either be handwritten, so it's obvious that you put it in, or it would be typed, but it's a font color other than black. Okay. That's what you do, and then you submit that. And the rule is the due date is 1 week from the lab. So if you have a lab on Tuesday, for instance, like we do this morning, I'm going to treat this lab as if it's midnight. So basically, I have to get this lab out to you by midnight on Tuesday, and that means you have to turn it back in by midnight Tuesday of next week. And Thursday, I'll do another lab, and I'll have to have that up by midnight, and you guys will have to have the lab report for that posted or turned in by a week from this coming Thursday. Okay, so that's how that works. Hopefully, this is self-explanatory with all these paragraphs that I put in here. If you have any questions, by all means, send them to me or send me a text message. That's the quickest way, but you can also ask me via email, stuff of that sort. Now, I'm going back down to week one module. There's the week one module again, but I'm going to the lab part, so I'm going to kill that. So I just showed you this. This is where you turn it in. I did not set the due date. Let me go ahead and do that real quick while you're here watching, just so you'll know. I'm going to say edit, and I'm going down here to the due date. I'm going to clear that out, and the due date is now going to be 1 week from Tuesday, so that'd be the 26th. And I'm going to leave it as 11:59 p.m. because that's going to be your deadline for, and I normally do it that as a deadline for all my online course assignments. It's 11:59 p.m. on whatever day. I'm trying to say midnight, but students forget whether midnight corresponds to the day before or the day after. Hopefully, y'all will eventually figure that out. But either way, that's why I'm doing it. Uh, as I also told you last night, though, I usually will not even take points off if you turn it in late, as long as when I start grading it, it's there. So if I go Tuesday night, or excuse me, Wednesday night of next week and start to grade this first lab, if I get to your lab and it's not there, you're going to get a zero. And then if you turn it in later, I'm going to take off points for it being late. However, if I did it, let's say Thursday, and you didn't get it until Wednesday, I'm not going to take off points. Okay, I just usually don't do that. I'm not required not to, but that's what I generally do. Okay, so now I'm going to go back to the module again now that we've changed that date. And again, lab one, week one lab module. So this intro to lab is the actual write-up, and this is the comments that I told you should look at before you turn in your lab, just to make sure you didn't make any of these mistakes that you see here. This these lab accoutrements, these are all videos and things that the lab manual the lab manual or the lab addendum, which is right here, they're going to have you use these things to actually come up with the data that you need. So what you really need to read is this addendum after you read this intro to lab, and then as you're trying to do the lab, you're going to need these videos, and this significant digit rules is a document to teach you how to do sig figs. This is a link to a video that teaches you to understand that sig figs is a first order attempt at doing things responsibly, but it's not really the proper way to do it. There's actually a more intense way called propagation of error that you deal with sig figs, and we'll teach you that. In fact, the very next lab is propagation of error, and I'll teach you that then. But the main thing is you need to know that sig figs is the low hanging fruit, and it's the bare minimum you have to do on all your labs. So you don't want to turn in a number that has more sig figs than you're supposed to have. You don't want to turn in a number that has fewer sig figs than you're supposed to have. All of those things will result in at least 5 points being taken away. The way you figure that out is, of course, you use the significant digit rules I explain here, and I explain in the lab as well. And then you might even look at this video to get some sense of exactly why sig fig work doesn't necessarily fail. And this is the addendum that makes this lab from a face-to-face lab into an online lab. So by having this intro to lab addendum, you're basically, this instructs you how to do this lab without the benefits of being in the actual lab room on campus. So let me go ahead and open this document so you can see what we're going to be doing. I'll zoom in a little bit, make that bigger. So to perform several measurements is the purpose. To perform several measurements which require significant figures for an understanding of the results obtained. In particular, estimates will be obtained for pi, for g, gravitational acceleration, the magnitude of the acceleration of a falling mass near Earth's surface, and for the period of an oscillating spring. Apparatus, various cylindrical objects, 5 cans of different sizes. We'd actually supply those 5 cans for you in the lab, but since you're at home, you just go to your cabinet and look for, soup cans or whatever, and 5 different sizes is what we're looking for. As you'll see in the addendum, it'll tell you more about that, or even give you different numbers. You'll need masking tape, or some kind of tape that might come in handy. It's not absolutely critical that you have it. You can use a piece of string. You can actually use a piece of paper. Really, why they're wanting you to have that, or one of the reasons they're using to have that, is you can use that to wrap around an object and then measure its length, and that would be a way of directly or indirectly measuring the circumference. So that's part of what we're using it for. A ruler, the conical spring. These things are really what you're supposed to have if you're in the lab. As I said, the addendum will allow you not to have all that stuff and still be able to do the lab. So it opens up with significant figures. This is what it's telling you about what we call sig figs or significant digits. And it's a good explanation of it, and it tells you how to do things, but it's a little inexact. That's why I have that document that says significant digits. That document is a more thorough, appropriate teaching of sig figs, and it gets you out of any ambiguities the way I define it, whereas the way the textbook author defines it and the way these lab manuals tend to define it, it's a little bit ambiguous. For instance, you'll see literally like on probably your first test, maybe your first and your second test for that matter, you'll see a question that says something along the lines of the number 6000 has how many sig figs? And the answers will be 1 or 4 or 2 or 3 or ambiguous. Uh, because that bank of questions is the questions created by your textbook author, you want to make sure you answer in the way that your textbook author taught you, which is specifically that number 5,000 it has an ambiguous number of digits. But the way I define sig figs, it has exactly one digit period. Okay, so that's the difference. 5,000, 5000 written down like that is understood by the true definition of sig figs that I give you. It's understood to have exactly one sig fig. But when you answer that question on a test online or electronically or whatever, it's going to have a question like that, and you say the answer is ambiguous because, according to the author, when you have a number like 500 or 50 or 75 million, all those zeros are ambiguous as to whether they're significant or not. What my rule says is you first ask, is there a decimal present? If there if there isn't a decimal present, then the leftmost non-zero digit is the most significant digit, and the rightmost non-zero digit is the least significant digit. And all the digits between the most significant digit and the least significant digit, all of those numbers between are also significant, and that's how you determine what significant digits are. If there is a decimal present, then the leftmost non-zero digit is again the most significant digit, but the rightmost digit period, if there's a decimal present, the rightmost digit of any type is the least significant digit, and therefore you have the most significant digit to the least significant digit, and everything in between are significant digits. So that's the way I teach you guys to learn about significant digits and how to decide whether they are that. So you see that when I write 5,000, unless I explicitly take the time to write 5000 and then a dot for the period, unless I specifically take that time, then the number of sig figs is just one. It's that 5. However, if I do take the time to put that decimal there, then it becomes 4 sig figs. So just keep that in mind. You'll get that as you read the document and as you read this document as well. So remember, you've got this document as well as my significant digits PDF that's in here. Then the big rule is once you have sig figs, what do you do? So if you have two numbers that you measured and therefore they have a certain amount of error and a certain number of sig figs, then you have to take those two numbers and multiply them, or take those two numbers and add them, or take one of those numbers and divide it by another, or take the log of one of them, or something like that. Once you've done that, how many significant digits does the answer have? Well, that's part of the significant digit rules as well. And it turns out that when we multiply the answer that we're supposed to round our answer to should have the number of significant digits that's exactly the same to the factor or participant in the multiplication or division calculation that had the fewest sig figs. So if you multiplied a number that had 12 sig figs by a number that has 3 sig figs, then your answer has to come out to be rounded at 3 sig figs. If you had a number that had 12 sig figs and another number that had 3 sig figs, and you're dividing one by the other, again, multiplication and division, this is the rule, then you're forced to round the answer to 3 sig figs. Now, if you're going to do that kind of a calculation and then use that result for somewhere else, then you need to carry one extra digit in all those intermediate calculations, but track it by keeping, like, underline the one that's not significant that you're just keeping. So keep that for subsequent calculations, but when you ultimately turn in the number, you'd want to turn it in with the right number of sig figs, or if you add extra sig figs, then I want you to underline each extra digit, so I'll know that you know it's not a sig fig. So that's the rule with multiplication and division. The factor or the quotient or the variable, whatever the quantities are that you're using to multiply or divide by one another, the one with the fewest sig figs dictates the number of sig figs the answer should be reported as. Okay. In adding and subtracting, it's not about sig figs. It's about basically how many decimal places do you have. And I say decimal places, but remember a number like 250, if there's not a decimal point by next to it by my definitions, then 250 only has 2 sig figs, and that would be the 2 and the 5. And the decimal place, as I say, for that number is in the ones place, or excuse me, I said 250. It's in the tens place. So the 5 is in the tenths place, or excuse me, the tens place, and the 2 is in the hundreds place. So the most significant digit is in the hundreds place. The least significant digit is in the tens place, and that means the decimal places is indicated by the basically the tens place. Okay, so if I add that number 250, which is only significant up to the tens digit, to another number that is accurate to, say, the first decimal place, then I have to round the answer to the tens place. So that's what happens with addition and subtraction. The one with the least precise number, in other words, the one that has the fewest number of quote-unquote decimal places, dictates the number of quote-unquote decimal places the answer has after you add or subtract. And then the final rule is if you take any number with a certain number of sig figs and you let a function operate on it, like taking the sine of a number, or taking the log of a number, or taking the cosine of a number, or raising a number to the e power or something like that, then the rule is the result should have exactly the same number of sig figs as the quantity that you put into the function. So for instance, whatever you substituted into sine or cosine or tangent or logarithm or e to the x, however many sig figs that had, the answer should have that many as well. Again, remember, keep an extra digit for all calculations. You don't want to catch yourself rounding multiple times, so you always want to keep at least one extra digit for intermediate calculations, even though the final report should have exactly the right number of sig figs, or any extra digit should be underlined so I'll know that you are not calling them significant. So hopefully that, along with this reading, will give you a little bit of a description. I know it's, when I'm just verbalizing these things, I know it's not easy to follow. If you were able to follow it, great. If you're not, that's okay, because you're still going to read it. And not only that, you can always pause this video and write down something to make sense of one of the sentences I say, and then play the next sentence, and then another sentence I say, listen to that, and then write down something to help you, and then listen to the next sentence I say, so on and so forth. So between all that, you should be able to figure out how the significant digits are working. Here's the when multiplying or dividing rule, and there's the with adding and subtracting rule. They don't tell you the other one that I told you about for taking the sine and cosine, at least not as a separate rule. So that's me giving it to you. But all of that, again, is in that other document that I showed you, the PDF on sig figs. Now, when you do take a series of measurements of one quantity, let's say the mass of an object or the length of a rod or something, then since you've taken multiple ones, it's important to know what is the value that we're going to pretend this value corresponds to. In other words, the ideal is that we're trying to, let's say, measure the length of some rod. So you measure it with vernier calipers, and then you write down that number. Then you take the vernier calipers off, maybe close them, then open them back up, measure it again, write down that number, close them, remove it, go back, open it up again, measure it again, get another measurement, write that down. Keep doing that till you have however many trials you want to do. Five is sort of the bare minimum. Sometimes three is, we'll consider three to be the bare minimum, but normally five is better. But once you've done all that, now what is the best estimate of the length of that rod? Well, it turns out the very best, and you're not going to do this, but the very best would be a weighted average, where you'd have to take the first measurement and figure out how much uncertainty there was in that particular lab or whatever that did that measurement, and you would weight it according to that precision that lab has. So if the lab is particularly good, it would have a extremely low uh, error in it, and therefore you would give it more weight. And you do that by a weighted average, basically the percent times the number plus the percent times the number plus the percent times the number divided by the sum of all the percents. That's a weighted average. That's the holy grail of the best estimate, but you're never going to do that in this lab. So I'm just telling you that to be complete, to let you understand that a weighted average is the high point of best estimates. That being said, what we're almost always going to use is just the average as the best estimate, and that's what they're saying here. The average is the best estimate. So if you take 20 measurements, you add those 20 and divide it by 20, add those 20 measurements to each other, and then divide that result by 20, and that'll give you the best estimate. Percent difference is basically you take the absolute difference between the values. What I mean by that is, let's say you are trying to test conservation of momentum. Okay, so you have a momentum that's a certain number of kilogram meters per second before a collision, and then you have another number that's the kilogram meters per second from after the collision. And in order for you to see whether angular or whether linear momentum is actually conserved, then what you'd want to do is compare the two values to each other. This would be a setup where you might push a car along, for instance, and that's going to be the thing that has the momentum, and its momentum is mass times velocity, and obviously that mass is dependent on which object you chose, and the velocity is dependent on how fast you pushed it. So it's not like you can go look up these values in a book somewhere. So there's no quote unquote accepted value. There's no value that everybody's agreed to. So this is something where you can't do a percent error. You can only do a percent difference. So what you do is you take the absolute value of the difference between the let's say the momentum before the collision and the momentum after the collision. So you say, here's my momentum before minus here's my momentum after, and then take the absolute value of that so it always comes positive. And then there's no good reason for any of them to either of those to be considered the accepted value like you would with percent error. So the best estimate is the average of the two, because you're going on the assumption that this is a system in which momentum should be conserved. So the average of the two is the most likely culprit for them. So that's why you calculate the percent difference by the absolute difference, which again is absolute value bars around one data point minus the other, and then you're going to divide that by the average of the two data points, and then you're going to multiply by 100 to turn that decimal into a percent. So that's a percent difference, and that gives you an explanation when you use it. Here's an example. For instance, if you tried to measure gravitational acceleration, the two values you got were 9.78 and 9.65. We know that value is supposed to be 9.80, but we don't necessarily know that that's what they were doing, so they're using percent difference to do it. It's not a good example to use. It's just a good example because it's one of the few numbers that students already know about coming into physics. Chances are you probably would just be calculating a percent error if you're doing an experiment for G. Now, what they could be doing is some kind of experiment in which they're testing gravity in two different physical scenarios that they suspect should cause the gravity gravitational constant to possibly change, in that case, yeah, a percent difference would be relevant because you don't want it to compare to the 9.8. That's, the acceleration in free fall when there's no air resistance and that sort of thing. So maybe that's why. But the main thing is, you just do the absolute value. What I tell my students is instead of worrying about absolute value, just do big number minus small number. So in this case, I do 9.78 minus 9.65, and it automatically get a positive value because the 9.78 is bigger than 9.65. And then, of course, you divide it by the average of the two, and then you multiply by 100 to make it into a percent. Now, normally, if it's 1%, so 1.1, 1.0, 1.2, 1.3, 1.4, 1.5, sometimes those numbers are such that you'd want to go ahead and report it to two sig figs. So if you come up with the ballpark of 1%, I'm going to accept 1.0%, 1.1%, 1.2%, 1.3%, 1.4, 1.5, 1.6, 1.7, 1.8, 1.9%, but I'll also accept 1%, 2%, that sort of thing straight up with just one digit. At the 1%, it's reasonable to have two sig figs, but at the higher percentages, it's not reasonable. One is sufficient. If you want to just stick to the sig figs, I'm not going to take off for that either. So if you actually do this calculation and use significant digit rules to round it, then I'm completely cool with that. In this case, notice if you subtracted 9.65 from 9.78, that's a difference of 0.13. Yeah, 0.13. So you took those three sig fig numbers and subtracted them and got a result that was only two sig figs. And then you're going to divide it by three sig figs added to three sig figs is still going to give us three decimal places or two decimal places and therefore three sig figs. Well, actually, you end up getting into four sig figs because the 9 and 9 brings you over 9. So it's going to be basically 18 plus 0.78 plus 0.65. So that makes it four sig figs, but you've already been throttled down to two sig figs from the subtraction, so you have to report it as two sig figs. I'm not going to take off if you use the sig figs rule, or I'm not going to take off if you decide to only use one sig fig with 1%, and I'm not going to take off if you decide to use two sig figs for 1%. But if you do something like wild where you use four sig figs and that's not justified, then yeah, there are going to be points taken off. Okay. Percent error is the other value that we can use to test how good our data is. Remember, percent difference is how close two things are to each other, not necessarily to some standard. Percent error is used when you're measuring how close something is to a standard. So what you do is you take the measured value minus the accepted, and then you divide by the accepted. So for instance, if you were using this data, the 9.78 meters per second, if that was your data for the gravitational acceleration, then you'd take measured, which is 9.78, minus accepted, which is 9.80, and divide it by 9.80. 9.78 minus 9.80 is 0.02. Notice that you've now reduced your sig figs to only one sig fig by doing that subtraction. And then you're going to divide it by 9.80, which has three sig figs, so it's still only going to have one sig fig. And then you move the decimal two places to the left by multiplying by 100, and that's going to inevitably, with this particular trial, 9.78, 9.80, that's going to be allow you to only present one sig fig in the percent error calculation. But that's how you do it. And the negative, I don't care if you include the negative or not. A lot of people do. So in future labs, remember it's measured minus accepted, and they might actually want the sign. I usually just tell my students just to take the positive value and turn that in. But you're welcome to turn in negatives. I'm not gonna take off for that. I will take off if you turn in a negative for percent difference because that's exactly wrong. You can't get a negative on percent difference. So keep that in mind. So the first part of the lab is going to be estimating pi, where basically you're going to take a certain number of objects that are cylindrical, and you're going to measure their diameter, and you're going to measure their circumference, and then remember that circumference is equal to pi times diameter, so pi should be equal to the circumference divided by diameter, so you can do that way. after that, you're going to find gravitational acceleration, and you're going to use this equation that you'll learn about in chapter two. But right now, you're just going to pretend like you know it and don't worry about it. But the deal is, you'll take like a golf ball or something, and you'll hold it up at 2 meters above the ground, and then you're going to time it with a stopwatch. And ideally, this would be something that you do it with a second person, so that one person can work the stopwatch and the other person can drop the object. But you want to, mark it with some tape on the wall or something like that. Hold the bottom edge of the ball that you're dropping exactly in line with the 2 meter mark. So the bottom should line up with the pencil mark or the tape or whatever. And you're going to drop it, and someone's going to start the stopwatch, and then when it hits the ground, they're going to stop the stopwatch, and that should give you a rough estimate of how long it took to fall. Now, it tells you explicitly when you're doing this, if you find a value that of time that's not between, I think it's zero point 0.6 and zero point 0.7 seconds, 0.60 and zero point 0.70 seconds, then you shouldn't count that data. That's just too riddled with reflex error. Okay, so you're just a little too slow, and you maybe made the measurement way too long, or you might have actually jumped. For instance, when people are watching something get ready to hit the ground, they sort of tense up and sometimes will hit the button a little early, and that could cause you to get a time of like zero point 0.5 seconds instead of 0.6 seconds. So the only acceptable data that you're going to keep is 0.60, 0.61, 0.62, 0.63, 0.64, 0.65, 0.66, 0.67, 0.68, 0.69, and 0.70. If it's outside of that, you don't record it. Then you're going to do oscillations of a spring to get an idea of what a period is, that sort of thing. So these are just the intros to what you're doing and the procedure. But again, you're given this information as if you're doing it in a lab. So I'm going to show you the addendum in a second. The final thing you're going to do, again, in this case, you don't actually have the masses, so we're giving you the data, but you're going to take a couple of those old metal 100-gram masses that you've probably seen in labs before. They're always beat up, got dents in them, scratches, they're old, that sort of thing. One common thought that I had myself is that I can't believe they're saying that these weights are sufficient to properly measure this thing, because clearly there's a butt ton of error with all these dents and scratches and stuff. Well, this is going to alleviate that concern from there on out, because what you're going to do is take two 100-gram masses, put them together and weigh them, which in fact we're just going to give you the data for us doing it. Then you're going to take two other ones and do the same thing, and then you're going to compare them using a percent difference. And what you'll see is the percent difference is really, really, really small. In lab settings, you want your lab results to be within 1 to maybe 5%, but in this class, I would say never higher than 12%. If a lab comes out with an error of 12% or more, it's almost certain that you did something wrong. It's not that your data was that bad. It's almost 100% certain that you screwed up. So keep that in mind. If you ever get over 12%, you might want to look back at how you did something, ask a fellow classmate, see if they got the 12%. Preferably, you'd start with someone else in your lab group if you had a lab group. But you can also just communicate with each other. So I'll put up a discussion board where y'all can meet each other at that as well, and y'all can talk about it that way. But the main thing is you want to make sure everybody's having those problems. And if you've talked to your classmates and still didn't get a decent answer, you can then ask me, of course. Okay. If you don't know of any classmates, you haven't figured out a way to contact any classmates, or if you tried to contact them and nobody replied, by all means ask me. I'm not saying you have to ask me last. I'm just saying it's better if you guys learn it on your own by peer instruction or help by your peers. But anyways, that's the last part of the data or the lab. And what you see is here's our data tables. So in this case, this is where you have your, in the lab, it would be 5 different cans, say, and you call them, can 1, can 2, can 3, can 4. You measure the circumference and you measure the diameter. And then from that, your pi value is taking the circumference and dividing by the diameter, and you put it right there. And you take this circumference divided by this diameter, and you put it right there. And you take this circumference and this divided by this diameter, and you put it right here in this third line. Ideally, what's supposed supposed to happen at that point is you will have these five filled out from your lab, but then you'll talk to other people in the class, and they'll give you their average of their lab. So, for instance, they got five values, and your best estimate, of course, is the average. So the other classes can give you their average, and you put it in this slot. Another student in your class can give you this their average, and you put it in this slot. Another one this slot, and so on and so forth. We're not interacting with each other this way, so this part doesn't need to be done. You do not have to include these two columns of data. You just need the five for yours. And then you're going to notice it says show your work. Uh, you're going to calculate the best estimate. That's the first time you've done a calculation, and this calculation is going to be a average. So you have to do a sample calculation for an average there, and that would be under this show work category. And then this is where you'd round it to the appropriate number of digits. Or if you want to, you can put all the appropriate digits and add one extra one with an underline under it, or two extra ones, or three extra ones with an underline under it. Just as long as they're underlined, I know you're saying they're not sig figs, and that will be okay. I won't take off points. They also ask you, of course, to calculate the percent difference. I was actually looking at the wrong part there. It's right up here. There. So what is the best estimate for pi as determined by your group? Find the percent error where the accepted value is 3.14. So when you get done with this, you're going to calculate percent error using that formula that I just taught you a few minutes ago, and that's a new type of calculation. So you're going to show me your work here as well. Again, you can do it by hand and show me putting the numbers in with their unit, show the math working out, and then go ahead and take a picture of that and then paste that picture into the Word document. You can paste it right here, or you could just click down and paste it at the top of the next page. That would be as fine as well. The main thing is I don't want it left to the very end. I want it right here where you had to do the calculation. Okay. Then for the distance of fall, what you're going to do is realize every time you drop it, the fall is going to be the same, 2.00 meters. And technically you could, if you were using a meter stick, you could get 2.000 meters. You should be able to get three decimal places when talking in meters, okay, and using a meter stick or something marked like a meter stick. But you'll put your time of falls here. Remember, just keeping the ones that are between zero point 0.6 and zero point 0.7, and then what you're going to do is calculate h over t squared, which is what they're showing you here. H over t squared is supposed to be 1/2 g. Okay, g is 9.8, so 1/2, or 9.80, so 1/2 of g is 4.90. So that's what you're shooting for as the accepted value, and you're going to calculate that by taking the 2 and dividing it by the square of this time, and you're going to put that in that box. You're going to take the 2 and divide it by the square of this time, and then put that in the box. So remember, you might want to take an extra step to do the square of the time, and then do 2 divided by that answer. If you try to square it afterwards, if you're not paying attention to your order of operations, your calculator will spit out the right answer, but it will be the wrong answer. It knows the right order of operations. If you do it and think the order of operations is one way, and you do a calculation that way, then you're going to get a wrong answer, even though the calculator did what it was supposed to do. Okay, so once you've got all of these, then you can calculate the best estimate, which again is the average, so that goes right there. That is an average, but you've already calculated an average, so you don't have to show that one. In this case, you sort of do just because it's telling you to show your work below, but normally you wouldn't have to. But since they said right here, show your work below, what they're wanting you to show me is one, taking 2.00 meters and dividing it by the time squared to get one of these box values. And two, you're going to take the average of all those. I've already seen an average, so I would say it's fine. But since they did say show your work here, maybe they want you to go ahead and show that in that one. I won't take off either way for that one if they show your work. But I would recommend, since they said show your work, you should do it. And then you're going to do a percent error, just like you did last time, percent error. So normally I would say you don't have to do that, but since it explicitly said show your work, you should do it. Okay. Again, not going to take off points because it's a little ambiguous or contradictory, but the fact that it says show your work should tell you that, oh, that work should be shown. And specifically, I think in this case, the way they wrote it is percent error blank show work below. That tells me that since they put the period afterwards, it looks like they might be talking about specifically just the percent error part. But even that's ambiguous, so I'm not really sure. Whereas here, they didn't do it like that. They said show work and put a colon. So that would tell me all this work is expected to be shown. Uh, but each type of calculation you do, as a bare minimum, I consider it important that you do the show me a sample calc for that. So calculating h over t squared is definitely something you hadn't calculated. So you definitely bare minimum have to show that. Uh, you're going to then watch a spring, a mass on a spring. So you take a mass and hang it on a spring, and once it reaches equilibrium, it'll hang at some height. But then if you just give the uh, mass a little pull to stretch the string just a little bit and then release it, it's going to go up, reach the max height, come back down, reach the minimum height, or reach the minimum height, and then back up, maximum height, and then minimum height, back up, so on and so forth. What you're going to do is watch it go from max height to max height again, to max height again, to max height again, and you're counting this again and again. And what you're going to do is let it go from max height to max height 10 times, and you're going to stop the stopwatch then. So first you start your stopwatch when it's either at its max height or its max minimal height, or you could do it at the equilibrium point, but that's not a clear indicator, so it's not safe to do that. So what you want to do is start the timer when the spring is completely stretched, or start the timer when the spring is completely compressed to its maximum value. One of those two, and then count to the next one. So if you're starting it when the spring is most compressed, you'll start it, and then when it gets most compressed again, that's 1, 2, 3, 4, 5, 6, like that. When you get to 10, you stop the stopwatch, and that'll be the time required for 10 oscillations. So you would record it right here for one trial. Then you look again. You could actually use the same video that we're watching. You can watch like the first 10, then you can watch maybe the second 10, and maybe the third 10, or you can even have them overlap. The main thing is you're going to do five particular counts of 10 oscillations, and then you're going to take the average of those five. You've already calculated average, so you don't have to show that to me again, but you're going to put right here for the average, the best estimate for the 10 oscillations. And then, of course, that's the time or the period for 10 oscillations. What we really want is something called the period, which is how long it takes one oscillation. So you're then going to take that number that you got for 10, best estimate of 10 oscillations, divide that by 10, and that's going to be what we call the period of the pendulum. By doing it over 10 cycles like that, we know that a one cycle is a short period of time, and there's going to be some reflex time that's delayed as a result of your brain not working as fast and your hands not working as fast. So if you take that duration of an error that's going to happen when it first starts, and it's also going to happen when you stop the timer, if you do that with 10 oscillations in between, then it's 1/10 as impactful. So that's why it's best to just do 10 of them and then divide by 10. So once you're done with that best estimate for 10, then you're going to divide it by 10, and that'll be your best estimate for one oscillation. And then here they say the mass of the first pair of masses, you put it right there. The mass of the second pair of masses, you put it right there. Again, the data in the addendum will give that to you. And then you calculate percent difference. You had already calculated a percent difference, but it says show your work here, so you need to show your work on that percent difference. Okay. All right, so that is the actual lab document that you're going to be completing, but you haven't seen the addendum yet that teaches you how to do it from home, and that's what I'm going to show you now. So here's the addendum, and it says estimating pi. So if you have a printer, or if you can get to campus where there's a printer, the main thing is you can print this out, and then you can use this very picture of a meter stick. You can use that as a measuring device. It's actually the right size. Okay. So you can just print this out, and you can now treat this as a meter stick that obviously goes from 0 centimeters, which is that point right there. Notice that's the 0 centimeter mark. It's not the end of the ruler. So if you want to measure, you measure from that little black mark, or if you're not comfortable being that close to a beat up edge, you could do it from the 10, from the 1, but then you always got to remember to subtract 1 centimeter from it. But you can measure all the way up to, 9 centimeters roughly, or 10 if you actually use that zero mark. And you can do it with just the paper. You don't have to have a ruler. It might be helpful for you to cut it out fairly smoothly right along this line, and then that way you can carry it around. You can wrap it around stuff to use it as a measure of circumference, all that good stuff. But it's what it says here. Estimating pi, you will pick 5 different cylinders from your home. That could be cylinders like flashlights, coffee mugs, soup. Uh, Soup cans, whatever kind of cylindrical stuff you can find. It could even be something like that handle of a broom or something like that. Even that works. So anything that has that cylindrical shape, which is basically a circular cross section and goes up, long as the cross section is circular, you can measure the circumference and divide it by the diameter, and that'll give you the actual value of pi. Uh, so that's what this says here with finding G. They're telling you to drop the ball 2 meters, and they're being kind enough to let you know that it's 6 foot 6.7 inches. So you could actually, if you don't have, obviously using this 10 centimeter ruler, you can use that. You can mark off 10 centimeters, put a little mark, and then use the 10 centimeters again, put a little mark. But you literally have to do that for 10 centimeters. You have to do that 10 times for 1 meter, and then you'd have to do another 10 times for 2 meters. And that might not be conducive. So if you have something at home to measure, like a tape measure or something like that, this isn't the best in the world because it's not measured in tenths of an inch, it's measured in sixteenths of an inch. But you could use that, and what they're telling you is 2 meters is 6 foot 6.7 inches. So you go all the way to 6 foot, which 6 times 12 is 72, right? Yeah, and then you measure an additional 6.7 inches past that, and now zero point 0.7. If you take that and multiply it by 16. 0.7 times 16, that's 0.1120, or excuse me, oh, it's 11.20. So when we say 6.7 inches, we mean 6 and 11/16 basically. So 6 inches plus 11/16 beyond. 11/16 would be 6.875. So that's a little small. They actually are wanting you to go 11.2 sixteenths. So you could say that would be the same thing as 12 or 22.4 30 seconds. So you can go up to the 11 seconds and then take the remainder of the 30 seconds, which is half a sixteenth, which you can figure out on a ruler and do that. But the main thing is you're wanting to get it pretty close to 6.7 inches larger than 6 feet. This lab has a short video of an oscillating spring. I actually give you two videos. One's a long one and one's a short one, if I remember correctly. But you can use those two videos to get the 5 trials. And since you don't have a digital mass balance, you can use the following data. So 199.77 grams was the mass of two of them, and the other two had a mass of 199.60 grams. So that's your data. That's it. That's the whole addendum. So it gives you a meter stick sample that you can use to actually measure things in case you don't have a ruler. It's not ideal to measure something as big as 2 meters, but it's certainly doable. And if you're patient and use tape or pencil marks or something like that with really fine lines, you can get it fairly precisely done from your floor. And then it's just a matter of you'll only be off by how much your floor is off level, and that's not going to be a huge amount. It shouldn't be unless you live in a really old house or something. Something bad's happening to your house right now. Which literally happened to me not too long ago with all my books. So, anyways, that's it. Anybody have any questions on what you're doing for this lab? I appreciate y'all coming. Again, you're not required to, but I do appreciate it, Mihak and Nathan.
No, I think that's good for me. Thank you.
You're welcome. You're free to go, but you're also free if you have any questions for me regarding any text material or anything we've talked about on the syllabus or anything like that. Y'all welcome to ask me those, or you're just free to go.
And the meeting for yesterday is going to be posted on YouTube, right?
Yes, I probably do it within the next hour. I've got to finish editing and then post it. And if you subscribe to my YouTube channel, it'll send you a notice every time I post something. You can unsubscribe later. I'm not making any money off of it. I'm not trying to sell you anything or anything. But if you subscribe that way, you'll get a message every time I post a new video.
Got it. And one last question. So I saw we were still doing mastering physics. I'm guessing the code and everything is on the Canvas.
So,
for that?
no, the way I have what's called a deeply integrated Canvas page with My Lab and Mastering. So you don't have like a course code, but you have a code that's associated with your purchase of a book. So that's called an access code. If you have that, then you can just click on the Pearson link on the left-hand side and go there, and they'll ask you for that. You type in that passcode, and it'll already know because you went through Canvas. It'll already know exactly what course to go to. In fact, if you try to go directly to my lab and mastering from the internet instead of through Canvas, you'll actually ruin my ability to determine your grade because I won't have access to it. It literally would lock me out. So make sure you never try to access my lab and mastering through the internet, but by first going through Canvas and then accessing it.
All right, sounds good. Thank you so much.
No problem. Have a good one.
Have a good one. Thank you.
Do you have anything, Nathan? Oh, he's gone too. All right. Well, that went pretty well. I think I explained the lab pretty well. It won't take much editing on this video, so I'll just post it, and I'll post the other one from last night as well. Thanks for coming, everyone. Have a good day, and look forward to having you the rest of the semester. Bye bye.